welcome to our talk about a competitive food retail architecture with microservices, where we want to show you what we did in the last 4 years and how we ended up with the architecture we are currently using. First, a little bit about ourselves or about the company we work for. We work for Rewe Group, and it's quite a big company, so it's big classic enterprise. It's about 57 billion turnover last year. It's about nearly 350,000 people working there. And all over Europe, we run about 15,000 shops. Most of the things, so the main areas are food retail, it's tourism as well, and do-it-yourself stores. The company was founded in 1927, so it's more than 90 years old. And maybe some of you can or will recognize some of those brands. Those are companies inside this enterprise. We too work for a digital hub in this enterprise, founded 2014. And this is basically where our journey started, so not 1927. It's only 4 years ago. And we want to show you what we did since then. So a short history where so this is a little bit, some things will be covered more in detail during the talk, but we want to give you a rough overview about the timeline and when things happened, and maybe you get the idea why we did some of the things. So we started in 2014 with we took over a monolithic developed e-commerce application. We worked with it with 2 teams, 2 developer teams, about 10 people working on it, and everything was in one code repository. And yeah, so we learned very fast that this is not going to work for a long time with the things we want to do. And later in 2014, the first colleague in an architectural position was hired, and the first task pretty much was think about what do we need to do to enable growth of the code base, of the developers, and of the business itself. Early 2015, he came up with a slight adaptation of the Spotify squad model and the idea of microservices to enable all those requirements. And in summer 2015, we had a meeting where we thought about, would it be a good idea to run Debian, to create Debian packages and use apt to install those Debian packages on bare metal hardware, or should we move to something more agile or more dynamic way? And we decided to go for Docker and Docker Swarm. In the first place, the decision was that we first want to learn how container worked and what are the pitfalls with containers. And this for we don't want to introduce Mesosphere or Kubernetes as a layer on top of it. So we first want to learn how this things works out. Beginning of 2016, we relaunched the mobile application, and this was basically the first application which was using all those created microservices until then. So the shop was still running very, very basically on the monolithic software, but the application was using all the microservices. You see there's quite some growth. So 2016, we were about 20 teams working on things. And later in 2016, it even grew further to about 30 teams. And we split it up into different domains like e-commerce, fulfillment, and big data. Late in 2017 and early 2018, we launched a marketplace based on our shop software and grew to about 50 teams. This is pretty much the size we have right now. So it's 45, 50 teams. And a few weeks ago, we launched a food fulfillment center, we call it, which is basically a warehouse optimized for food. So you have different temperature zones in there. And in the special case here is you also have a lot of automation in there, and the people are not running around in the warehouse anymore, but the goods are coming to the people to be picked in one place. When you have a look at the growth of services and teams, you probably get a better idea with this slide. So we started with one service or one software we had to maintain, 2 teams, and we ended up with about 270 services we are running right now in different platforms, and about 48, 50 teams maintaining and developing those services. A few words how this is all connected, and you will hear some of those words later on. On this slide, you can see 3 layers, basically, or 3 levels of this slide. The first one is the architectural design level. The second one, the pink one, is the technical description, and the gray one is the organizational view on the things. And when we start on the left side, we have one of the core domains. I already mentioned them. This is e-commerce, fulfillment and logistics, and big data. We are running right now. Those domains are served by one platform each, and on an organizational level, one unit we call a tribe is taking care of these platforms and the requirements of a domain. One domain consists of several subdomains. Subdomains at the moment don't have a technical equivalent. Maybe it could be a Google project later or something like this. But a group of teams is taking care of a subdomain, and this group of teams, the smaller group of teams, is something we call a squad. On the most fine level, we have one bounded context which describes one business requirement or one functionality we want to serve. This is done by one or more services, and one or more services are maintained maximum by one team, so we don't share services between teams, but a team can maintain multiple services.
So now, remember our architect had the task to scale this application, and our management said we want to have 30 or 40 teams working on this stuff. So what did he decide to do? It was pretty easy that we could not stay on this monolithic software, and he made up 2 major design goals. First one is called decentralization. So we wanted different teams to work on different code bases and to deploy independently from each other. So the first dependence should be at runtime and not before that. And the second design goal was vertical boundaries. So we didn't want to have a front-end team, a back-end team, and a database team, but we wanted to have business teams. So, for example, search or checkout or something, so that we have a bunch of people just caring about this stuff and to become specialists in this certain area. So these were the 2 major design goals he came up with. Now, this is a pretty mandatory slide for a microservice talk. I think most of you should have heard about Conway's law. So just shortly, Melvin Conway stated in the 1960s already that every organization that builds a system will always produce designs that have the structure as a copy of the organizational communication structure. So if you have a system like this and 4 teams like that, they will always build systems like that. And that means, on the other hand, that if you want to build vertical microservices, you first have to restructure your organization. And this is, for example, done like this. So these are just 6 random functionalities you want to have in your team. So front-end, QA, analytics, middleware, back-end, and ops. Could be even more. So if you want to have vertical teams, you need to have these functionalities in your team. And that doesn't necessarily mean that you have one front-end guy and one QA guy and one analytics guy, but these capabilities have to be in your team. And if you have a structure like this, then you can make teams of that. And if you want to grow further, then you need to staff another team which has these capabilities, and then you can go on. Okay, so now we realized how our teams should be structured and how our organization should look, but we didn't know at that time how to cut these teams. What is a good way to determine boundaries? So do you just do it randomly, or do you look at the data and say, oh, this team is taking care of this piece of data and this team is taking care of this piece of data? What we did is to look, we looked at our processes we have. So and the major process you have as an e-commerce company is the customer journey on your website. So the first thing the customer sees is the website itself, and this is a block or a squad we call site landing, and these people take care of welcoming the customer, and their stuff like login and registration and loyalty programs, for example, so that the customer comes comes back to our site. Then the second squad we call product discovery. That's about search and recommendation. And this block is pretty important for us because in a normal e-commerce website, people buy 2, 3, 4 items at one time. In our case, people buy 40 to 50 items because people do their week grocery shopping at our site. So if we have a lousy search functionality or something, people will take long and they will have a bad user experience and they will never come back. So it's pretty important for us to let people find the stuff they need quickly. The third block is checkout. It's pretty classic. We have payment in there and a shopping basket and the checkout process. And the last one is fulfillment. And that's again special because we don't put the food into a package and deliver it via DHL or something, but we have our own fleet and our own people deliver stuff to your doorstep. So there's a whole bunch of software needed to organize that. For example, it's routing, or it's all this warehouse stuff we have, and Ansgar already mentioned it. This squad grew so big that we decided to put a whole new core domain out of that. And there's just a little stub left. That's the fulfillment part that's still part of the user journey, but all this logistics stuff has been moved out into a whole new platform. And then, unfortunately, we have some horizontal layers and that didn't fit into the vertical part. So, for example, it's product information because all of these vertical blocks need product information in somehow, prices, pictures, and stuff, so we couldn't fit it into one of these blocks. Then we have back office. It's stuff for the marketing people or for customer services, for example. Then we have mobile, and we would have loved to put a mobile developer in each of these teams, but unfortunately, that's not how you deliver mobile apps, because in the app stores, you have to have one deliverable item in the end. So that's not how it works. So we need to have special mobile teams right now. Google is working right now on some kind of approach where we could do this otherwise, but for the meantime, that's how we need to do that. And finally, we have a platform squad that take care of, well, the platform and some services that don't have to that doesn't have to do with any business stuff. So, for example, just a generic mail relay or SMS relay or stuff like that. So now we were pretty sure how to organize ourselves and to cut our boundaries. Now imagine you have 30 or 40 teams, and they all have a whole tech stack in their power, from front end to database. And you want to be sure that people are building something consistent, because this can grow horribly if some people are doing things like that and another team does things like that. So now how do you guide the developers to build a consistent system? Well, the first point I already told you, we have these major design goals, vertical boundaries and decentralization, and it's pretty hard to violate them. We just tell the teams to not implement new features in the old legacy systems, but if you have a new thing coming up, then build up a new microservice or put it in another existing microservice. The next thing is we have architectural principles. It's just a collection of 9 basic laws, and it's less a rule set, but more a kind of a philosophy we want to give the developers. And these principles are around autonomy, automation, and communication. And on the next slides, we will go through each of these principles. And the last element is what we call guides. It's documents that describe really in detail how certain things must be done. Because our teams have a pretty high degree of freedom, they can choose which JVM language they want to have, they can choose which frameworks they want to use, and inside their context, they are pretty free to do stuff. But if it comes to communication or to interfaces, we need them to be to stuck to our rules. And these guides are, for example, about eventing, so asynchronous communication. We have REST guidelines, authentication, logging, and stuff. So everything that belongs to the whole system, we need to have guides for. So, and this is the first.
So yes, as Sebastian said, autonomy is one of the areas where we want to give guidance to the developers. And the important thing here to mention is that autonomy is not equivalent to anarchy. So you cannot do whatever you want to do, but you should be free to do things without interfering with others. So you're not, of course, you're not completely independent. You stay interdependent between the teams, and you have to organize this in some way. But in the end, the ultimate goal is to let the teams as much of the decisions do as they can do, and don't have to be big groups involvements and big meetings with everyone where we have to align everyone. So this is basically the things we want to encourage with those principles. So when we have a look at them, the first one is deploy independently. So everyone should be able to deploy a new service, an existing service, an update, whenever the team wants to deploy it. And they should do it in an autonomous way without interfering with others. So there shouldn't be a dependency. I can only deploy my service when your service is already deployed. So this is something we want to avoid, and we don't want to have, on the other side, teams coming to your team and say, you have to deploy because I have to deploy afterwards. So from both sides, this is something we really want to avoid, and where we strive extremely for this autonomy on level, on team level. So the next thing is to isolate failures. If something goes wrong, and there will be always something which is going wrong, this should only affect your team and your service, and all the other services around it and communicating with it should be resilient as possible to manage this error cases, and to be still able to work without recognizing the error in your service. So this is another thing which gives everyone autonomy. If you are resilient to errors from others, you can still go on with your work even if others fail. The next thing is hide implementation details, and this is about communication and sharing state especially. So everything which is affected which is maintained by your team should be encapsulated by your teams. There are ways to communicate with the outside world, but how you do things and what things you do to reach a goal should be inside your service, and you shouldn't be rely on state of other services to do something. So this gives you autonomy on this level. And the last one is encapsulate data storage. So we don't have one big database running where everyone is writing stuff into it and reading from other one's tables and reading other databases and stuff like this. For us, every service gets its own database. They might run on the same cluster, on the same database cluster infrastructure-wise, but you get your own database and no one is writing or reading from this database, then your service. Every access to this information is only provided via several APIs we will describe later on. This also enables the teams to choose the database technology they want to choose for a certain use case. So this gives you freedom on team level to make technical decisions. Of course, when you're striving for autonomy and you want to have really autonomous teams, there will be challenges. One of the bigger challenges we saw was not only on a technical level, but it was more on a product level. So when you see the customer journey and you want to have something implemented in this customer journey, it often spans several of those subdomains, several squads, several teams, because you want to have something look the same way on every page you want to display inside this customer journey. And this is where the product people have to think differently and have to learn how to reduce the scope of a feature and how to split up the feature into independent features which can be implemented by several teams at several points of time. So yeah, so this is something where you have to educate your product organization a little bit. To ease this autonomy up, we came up with certain data integration patterns, and one of them is to change your behavior depending on the data you get. So when you see you want to display a product detail page, and you need product data for this. So the product detail service gets data from product information. And depending on which data you get, if it's the old data model or the new data model, you can decide which page do I have to display for this certain product. And this is one way where you can enable other teams to deliver functionality later, because they can still provide the old data model. You can work with it, and as soon as the new data model arrives, you will display the new page automatically. Another thing that helped us was an evolving implementation. So we started with a simple solution in one team, for instance, the use of Apache Kafka, and the producers and consumers and all those things you need to do there, they were evolving through all the teams, a lot of teams using this. So the first team started with a solution which fits their use case. The next team adopted this solution and says, okay, I see your implementation, but here I can tweak it a little bit, give the information back to your original team. Your version is already better, and the first team can decide, when do I want to implement those changes? Do I want to implement them at all? Do I have a benefit from it, or do I stay at my implementation? So this is where your implementation evolves, the more teams doing this implementation, and in the end, finally you will end up with a library you built out of this, or you can share with other teams, but usually you want to avoid this in the very beginning, and you want to invest work to do this several times to learn from it, because you don't know everything in the very beginning. We talked already about the tech stack. So when you think about the 48 teams we have right now, we have a lot of Java running there. Most of the services are based on the JVM. So we have Scala, we have Clojure. A lot of services use Spring and Spring Boot. We also have Go in there. Kotlin is getting bigger and bigger. So we started with the mobile apps. It's also going into the backend side. And we have also infrastructure services running on Node.js. We have something on-prem, and the new projects are running in the Google Cloud. On-prem we use Ansible, and for data distribution between the services, we heavily rely on Apache Kafka. Automation is the next one. So when you think about automation, why is this important, and why do you want to put a note on this for every developer? If you want to be scalable, and you want to be scalable in a horizontally way, you don't want to deploy a new server every time. So you don't want to do this manually. You need to be scalable, you need to be fast scalable, and this means you need to automate things. The next one is stating exactly this. So all your tests, all your deployments, all your ops stuff should be automated as far as it can be automated. There shouldn't be someone pressing buttons or checking things or whatever you need to do. If you do it more than a few times, just automate it. And the last one in this area of interest is be highly observable. So when you deploy things, and 48 teams deploy 300 services several times a week, you want to get to know when something went wrong, and you want to get to know this very early. So it's not about only testing, but also have monitor your tests and monitor the results your tests gave, and you can even push this further and say, run the test also on the production state and see what happens to the actually production code and how this behaves, and then feed it back into monitoring solutions and see what happens to your products.
So the last two principles are about communication, and you can bet that communication between microservices gets pretty important. So there are basically two principles. I start with the second one. So we need to have standardized service communication. So we have some standards defined, and teams are stuck with these standards. So it's not possible that one team comes up and says, hey, we still think SOAP is a good idea, and if anybody wants to communicate with us, here's our WSDL. So that's not working. We just have 3 or 4 standards there. And the most important standard, even though we want to avoid it as much as possible, is REST. And we want, if teams are having a REST API, we want them to have to be in REST maturity level 2. So we need to have resources, and we need the correct HTTP verbs. So the second one states we want to avoid synchronous communication as far as possible. why is that? So a typical problem you have in HTTP REST-only architectures is something like this. Imagine there's a request coming in from the gateway, and for this request you have 5 microservices responsible. So the request comes to the first one, and he doesn't have all the data, so he needs to communicate to service 2 and 3, and service 2 needs to communicate to 4 and 5. And now imagine something is broken at service 4, and service 2 gets timeouts all the time. Then what happens? The service 2 waits until the timeout is done, so maybe 2 seconds or 1 second or something, and then it has to do something. Or if it's really worse, then you have all the threads in service 2 are stuck in waiting for the timeout of service 4, and then anything can happen. So something that help here are proper timeouts. So maybe a 2-second timeout isn't really good. Maybe 300 milliseconds is enough. Then every service should have fallbacks if the other service won't answer. So maybe I have done a blank space on the website or some text that states, please reload the page. We couldn't render this. We're sorry. What's even better are circuit breakers, so that each service that communicates synchronously to another one monitors the other service and checks if it's really up and running. But these are only things that tackle the problem a little bit, but they don't solve them. And the solution for us was to implement eventing, which is our name for asynchronous communication between microservices. So again, when we talk about API, we want to see something like this. So every microservice has 2 or up to 3 different APIs. First one is a REST API. It's synchronous API with a JSON payload. Then we have a UI API, and Ansgar will talk about this in the very end. And it's a synchronous endpoint with an HTML payload. And we have our event API, which is, in our case, Kafka. So the idea is now to have as much data locally as possible and to not be forced to talk to other services to fulfill requests. So we duplicate data a lot, and that's OK for us. And we do this up until we have problems with eventual consistency. So this is the only case where we don't rely on asynchronous communication. So I give a little example what we're doing here. So we, as I said, we use Apache Kafka. Now imagine we have a service called Customer Data Service, and he takes care about the customer's core data. And he has a REST interface and maybe some UI. And he has a database where all the customer data is lying inside. And every time the data changes, he pushes this change on a customer queue or a topic. And there might be another service, the invoice service, which is capable of rendering an invoice. And he obviously needs customer data because the invoice contains the name and the address and something. So he subscribes to this topic and stores the data inside its own database. And maybe there's another service, the checkout service, which needs maybe the delivery address of the customer. So he also subscribes to that and puts it into its own database. And if you see this picture, you would say that's just database replication. What we do on top of that is, if you look at the payload, we have here the customer ID, the name, loyalty ID, and 2 types of addresses, invoice and delivery address. And the invoice service is only interested in the invoice address and the name, so he just stores this piece of data. So he filters the stuff that he needs, so he doesn't have a full copy of the data, but only the stuff he needs. And the checkout service on the other side is only interested in delivery address and the name. So when we talk about eventing, we don't mean messaging, because an event is something that has to have happened already. So there's nothing that is about to happen or which is happening right now. So one service tells the other service what has happened inside its database. And what important is that there's only one owning service per queue. So if there would be 2, these services would have trouble to synchronize, and they need to be sure that they're working with the right version. So our rule is only one owning service, which is allowed to publish to such a queue. In our case, it's also important that we publish complete entities and not deltas. So our approach is not like event sourcing, where you can publish only the deltas. So we always provide the whole new entity. So if just one field has changed, even though we put the whole new entity on the queue. And the reason for this is mainly that at least in e-commerce we're still running at a local hoster in Germany, and even though it's 2018, it's obviously still a big problem to put another database into that rack. So we needed to save this space here, and we do that with a feature called log compaction by Kafka. So imagine we have one customer and he changes his data 100 times. So we have 100 messages lying on the broker, and with log compaction we tell Kafka to get rid of all the old versions and just keep the very recent version, and that saves a lot of disk space on the broker. Another feature we want to have is rewriting and rereading. So the publishing service needs to be able to rewrite. That's first because we don't treat Kafka as a database, and we even don't have a backup for that. So this is just for communication issues. So if the broker goes down and we have to set it up from the start, then each publishing service needs to push the data again onto Kafka. So we need every service to be able to rewrite on a click. And each service needs to be capable of rereading. So if one of their databases dies, they need to recover it all from Kafka. And we need it for another case. So for example, if the customer data service thinks, oh, maybe I have a new field for my customers, maybe the shoe size or something, then you can gather that data, and then you can republish all the records with this new field in it. And every one of the other services can decide, oh, I've heard there's a shoe size now on the queue, and they can decide to reread everything from the start, so they have the shoe size for all the customers in there. Okay. So there are some lessons we've learned with microservice APIs. First thing is, and I already told that eventing is an API as well. And when teams come up with new services, we tell them, plan to have all the APIs implemented in the first place. So what teams sometimes do, and that's what sometimes product owner push for that, is that the teams just build a REST API and they say, oh, we don't know of any other team that will consume our events, so we will implement the eventing stuff some weeks later. And then some weeks later, another team comes along and they say, hey, we would like to consume your data, but you don't have events right now. Could you please implement that? And then say, oh, our backlog is full, maybe next year or something. And that's not what we want to have. So we tell the teams to build a whole API, and that means synchronous and asynchronous. Second thing is, writing APIs isn't really easy because teams tend to write APIs for special clients. In our case, Ansgar told that already, our mobile application was the first one to use all these microservices. And during that time, the mobile team went to other teams and asked them to publish the API in their special way. And they say, oh, that's already cool, but we need this to be so-and-so because in our mobile case, this is important. And teams did that, and this crashed when the second client came along, so our browser application or terminal application. And then teams had to redesign their APIs to fulfill all the clients. So writing a generic API isn't really that easy. And the third thing is breaking changes are really a problem. So we tell teams to avoid breaking changes as long as possible. And by breaking change, we mean not adding a field. Adding a field must always be okay. So consumer will ignore that field, but renaming fields, deleting fields, or restructure the whole payload is a problem. And we ask teams to avoid that as long as possible, and in some cases it's possible to avoid that and to find other solutions. And only if there's no other solution, we allow them to make this breaking change, and that means they have to put up a second API or a second Kafka topic, ask all the clients to move to that other topic, and then finally get rid of the old one. And that's really painful if there are 20 or 30 teams belonging on this API. So
the last thing is, how do you access all those microservices? And we heard a few things already. No one is accessing from the outside the event streams we have inside this application, but maybe some REST APIs are exposed, or especially in an e-commerce environment, the web page is an exposure of all your services. So What we have is we have basically 3 types of gateways we maintain. The first one is a terminal, is something we call terminal gateway, and by terminal, this is something you put into your stores. So we have the grocery stores, and you can, in the entry of the store, you can check your loyalty card, you can check your points on the loyalty card, you can get recipes from there and stuff like this, which might inspire you inside the store. So content we provide inside the stores. These are the terminals in the stores. The next one is the UI gateway, which we will see in the next slides in a more detailed way. And the last one is the mobile or API gateways, which are capable of serving APIs to the clients that need those APIs on the outside. All those gateways have basically 3 functionalities. They can compose things and combine requests into one single response, so the client doesn't have to do 20, 30, 40 requests. The gateways can combine those requests and get all the data from the microservices and hand out one response or less than 40 responses. They can route to the service which is responsible for this response, and they do all those security things. They authenticate, they know which user is requesting the information and which information can I provide to this user and stuff like this. So let's have a look at the web page. It's in German, but I think this is not important for the page. You see a product detail page of our shop, and you see several things on there. First, you have the page at all. This is the pink border you see here. On the very top, you see a search bar, which is maintained by the search team. You see the basket on the top right side, where you see the basket flyout with all the products you have, maintained by the basket team. You see some categories and navigation, which is maintained by the navigation team. All this is combined by a team which is taking care of the header itself. Then you have the product detail information, which are served from the product detail team. And inside this block, you still have the Add to Basket button on the right side. And guess what? It's an Add to Basket button. Who's taking care of the basket? It's the basket team. And the special thing here is that we managed to write a software which can combine all those microservices and not asking only for data from those microservices, but this gateway component is able to get front-end snippets from those microservices. So it's able to get HTML, CSS, and JavaScript and put all this together into one page. So for us, this looks like a little bit like the missing link we didn't found a few years ago for microservices. You always heard about combining REST calls and send it out, and you hear about different REST applications and switch between applications, but you didn't find a solution to combine it all in one page. There are solutions like BigPipe from Facebook, but they are doing it on the client side, and this is working on the server side. So what happens on this page? The request comes in from the browser, and it enters the gateway, which we call dynamic UI composition. And the first thing this gateway does, it authenticates the requests, it gets information about the session, about the customer, whatever is needed. It enriches the request itself, so it puts header in there, puts more information in this request. It determines, is the customer part of a test group? Does he belong to a special zip code or something like this? Puts information about this into the requests, and then it looks up the route for which service is responsible. So in this case, when we have a look at this page, the product detail team would be responsible for the overall page. So the next request is the request 6, which is asking service A, in this case, the product detail service, please give me the overall template of the page. And the service is maintained by one team, and this team can say, okay, here is the overall template of the page, and they put all information into this page they already know. They say, I know this is a product detail page for bananas, and this, I know the picture, I know the description, I know the ingredients and all the things from the product itself. This is what product details are. I can provide them already, and there is HTML pictures in there and stuff like this. But they also say, I know the price, but I know there needs to be a place where someone can add it to its basket. And they're just describing this place and say, here you need to take care of something. And I don't know what, but here you need to put an add to basket button. And they also say, here you need to put the header. And then when we have a look at this, this template gets back to this infrastructure component, the pink one, and it parses the template and goes through all those includes it founds. And this can be recursive, so it first finds the header, and then it gets the details about the header and asks about the search bar, about the navigation, and all the other things we saw in the header. And if everything comes together to this, and this happens asynchronously, or the services are asked at once, you have all the information together, you can put them into one page. The CSS is scoped in here, so you don't interfere with other containers inside the layout. The JavaScript is put in there in the right order, and it's also scoped through modules, and then you can send back the response to the browser, and you get this page in total, but you don't know in the end that this is served from different microservices, and this combination is happening on the front-end side. And basically, that's it from our side. We have a GitHub repo here where we are working from time to time, where you can see this integration patterns we described, where you can see how we use Apache Kafka, where you can see how this front-end integration works. So on our side, in the production environment, it's a Node.js application. I think the colleagues are working on open sourcing it, but they still need some time to do so. And but here you will find a Java implementation, which a little bit less functionalities in there. But you can have a look at the code and get the idea how this things work out. Yeah. So we have 5-6 minutes left. Thank you from our side. And one last thing. So use the JFall app, and if you like our talk, vote for the talk in the app, and if you don't, just ignore it. Thank you very much. So we have 5-6 minutes left. If there are any questions, we are happy to answer. I already see one.
Forever.
Yes.
So the question was, how long do we keep the messages on the queue? So if we don't configure otherwise, the messages stay there forever. So, and this is important because we have new services coming up and they need to replay everything that's on the queue. So we cannot just throw stuff away. There are some certain queues, for example, orders, where we say, okay, maybe it's not that important that every service knows 6 year old orders. Maybe we cut them at some time and just keep the last year or the last 2 years. But as a default, we keep the data forever.
So in the logistics area, when you think about a warehouse and you have a lot of movements in the warehouse, then you won't store any historic data anymore. So there you can reduce it even to days or weeks. If you think about stock movements you're doing, it's 500,000 events producing every day. Then you just throw them away when they are processed, and you don't have this historic data. But this also means in half a year, if a new service comes up and says, I have a brilliant idea how to optimize stock handling in a warehouse, but I need all this historic data where we moved stock around, then it's not available. So this is the compromise you have to do. Further questions? First, yeah? So the question is, the pink box we see here, which technologies did we use to build this middleware infrastructure component? This is basically written in Node.js, and as far as I know, there were experiments about the parsing and stuff like this to do some C code in there to get really fast and build Node modules from it, and so native compiled modules you can include. Actually, I'm not sure about this state, but they tried it, And but this is still a Node.js application, and I think it's Express, which is handling most of the requests.
I think the team found out that I/O with Node.js is pretty fast. So these are really small containers, and I think we have 15 or 20 from them running, and it's not a problem for the infrastructure. So we can really do good horizontal scaling with that.
And there was another question in the middle. One low, one right low. Yes. No, one behind you. Next one.
Right.
You don't want to know. So the question is, we started in 2014, and what was the legacy system running on where we started from? Shall we say it? So it was Java, and it was a struts application which served the front end, and yeah, but it was still one Java application.
And it's still running. We have still 2 pages that are rendered on this machine, and a few people are losing their bets again at the end of the year, and they have to buy some boxes of beer because it's still there. It's like it's a little bit like a zombie.
You can try to kill it, but you never get rid of it. Yeah.
How did you go about testing contracts? Because I see quite some interaction and consumers stuff now.
Again, with the first part.
Testing the context of the services.
Yeah. There are some teams that have contract with each other, and that we do client-side contract testing, but it's not the case all over. So we don't force it. So what we want is we want to have stable APIs, and we need teams to look for breaking changes. And so far, nothing really bad happened.
So, so the question was about contract testing between all those REST interfaces. And when you think about the very beginning, where Sebastian showed the customer journey and the different squads they are working in, we try to avoid communication, or we really forbid communication between those squads. So if communication happens from service to service, it happens to a service right next to you, which is maintained by your team or maybe by the team sitting on your desk. So, and they have to talk to each other. But in the end, the goal is to not have synchronous communication at all. There are cases where you cannot avoid it. So in the checkout phase, you probably need the delivery address to present a time slot, which is depending on the address and will change if you change the address. But basically, we try to avoid synchronous communication wherever we can. More questions? Yes?
Regarding the data duplication amongst the services, do you have any procedure in place to ensure that the data is consistent over all data sources?
It will be in some time. So the question is about data consistency when we spread the data throughout all the services. It's not consistent immediately. So the moment you write it to your database of the owning service, product details written to the product detail database, no one else knows about it, because you first have to publish an event to tell everyone, hey, I created a new product, and then everyone else has to consume this event, process this event, remove information the service doesn't need, or transform it to fit into the data model the service needs, or transform it from something which looks like, it's the other way around. So I was thinking, but you get a JSON document and you need to transform it to put it into a relational database, for instance. And this takes time. So there is a time span when the new product is not available for everyone, and it's probably it will be shown on the shop, but you cannot put it into the basket because the basket doesn't know about the product. So this might happen from time to time. And in the end, everything needs to be published, and you need to consume. And this is where we have a separate talk about how we do eventing and how we ensure that the information from Apache Kafka is produced in a proper way. So you make sure that the producer is safe. And we also found ways to make the consumers very safe and not missing any messages. So we are not talking about events like click events on the website where you say, I don't care about if I miss 2 or 3. We need to make sure that the consumers get every event and process every event. Does this?
Yeah, I was aware of the temporal aspect of the eventual consistency.
Yeah.
In the end, things may go wrong when you cannot really store your data, and you can.
Then you don't commit the read to Kafka. So if you cannot store it if the consumer cannot store it into its own database, then you don't commit, I have read this. Then you get it next time you try, and then your database might be there. My phone shows me we are out of time. We are out of time. Thank you very much for the questions. Of course, we still will be around for some time, so if you have questions, just come down to us. And thank you very much.
Thanks.